Our first speaker today is Nilanjan Mukherjee, Senior Director of Engineering for Tessent Silicon Lifecycle Solutions. Nilanjan is currently involved in the research and development of key technologies in the area of test quality, test compression, logic bits, and silicon lifecycle management. He is a co-inventor and an architect of Tessent Test Compress, the VersaPoint Test Points technology, and the Observation Scan technology. Welcome to the stage, Nilanjan.
Good morning, everyone. Welcome to ITC 2023. My name is Nilanjan, and I again welcome you to the Diamond event hosted by Siemens DISW. So the topic of my talk today will be advances in Shift Left DFT, how our customers are actually using the DFT implementation or implementing DFT in RTL to enhance or to able to verify in RTL, thereby reducing the time to market. The agenda of my talk will be as follows. I'll start by talking about some of the challenges of growing time to market. Then I will address some of the solutions that can actually help alleviate those challenges. I'll briefly mention about the shift left evolution, then talk about the tools for RTL DFT implementation, and finally summarize. So if you look at the graph, the left side, the left graph, it actually, to meet the society's demand for semiconductor ICs, the number of ASIC design starts has been growing steadily over the last 7 years, and it is expected to grow at a CAGR of 5% in the near future. On the right side, the graph shows the challenges, the engineering effort that is needed to implement an IC as we move towards lower technology nodes. As we move from 7 nanometer to 5 to 3 to 2 nanometer designs, the amount of engineering effort that is needed increases by 55% for every node. The way we are addressing it today, we are throwing in more engineers, more bodies to do that work. But that may not be sustainable. That is not sustainable. And what is exacerbating is that problem is the availability of skilled resources that can work in the engineering, in the semiconductor design industry. So this is a study that was that BC did, the Boston Consulting Group came up with, which showed that by the year 2030, the number of skilled workers that are needed in the semiconductor industry will grow by 50%. Whereas the number of skilled engineers that we will be producing will grow only at 1% rate. So by 2030, there will be a shortage of engineers by at least 35%. So just throwing in more engineers to the complexity, as the complexity of the design increases, is not a scalable approach. So what did we do? What are some of the challenges of growing time to market? If you look at it, the factors that affect the time to market are the design, technology, and system scaling. So as we move to lower technology nodes, like for example, FinFET to gate-all-around to nanosheets, the complexity of the design is increasing. Similarly, the design complexity, if you look at just the design complexity, how do we now partition the designs so that it can actually fit into multiple dies to get into, basically go into 2.5D or 3D IC packages? That is also putting pressure on the time to market. And then, as I already mentioned, the lack of skilled resources is creating or exacerbating this entire pressure on the time to market. So how do we address some of these challenges? So there are some proven strategies or proven technologies that are already being used across the industry. So one such is the hierarchical DFT techniques, right? You can implement DFT across, like at the board or the tile or the core level, so that you can actually parallelize the activity across design teams or across geographic locations and reduce the total implementation time. That not only reduces your implementation time, it also reduces the amount of the machinery, the machinery that is needed to complete the task. Similarly, shift left as another strategy where we see companies are increasingly doing some of the tasks or some of the DFT implementation in RTL rather than at the gate level. So that improves the design cycle time because it reduces the number of iterations that you need to do when you find problems later in the design cycle. And then finally, with the lack of skilled engineering resources, we need automation. There's a lot of talk about expert systems, AI, how that can help improve the productivity of the DFT and the design implementation teams. So if you look at the requirements for shift left DFT methodology, what are some of the key requirements? So those can be divided into three categories. First is analysis, insertion, and verification. So on analysis side, if you are doing DFT implementation, you would like to understand you'd like to run some of the design rule checks at RTL. You'd like to understand the complexity of the RTL in terms of and how it contributes to testability. You would also want to do things like test point analysis early in the design cycle, wrapper analysis to isolate your cores, or even X-bounding analysis to improve compression or actually block all the excess so that you can implement logic-based. As part of insertion, you want to insert all the test instruments early in the design cycle in your design so that you can verify as much as possible. You would also like to have tools that can actually edit your designs and deal with some of the complex constructs, the system Verilog or the Verilog system Verilog constructs in your design. And also one of the most important things is you want the tools to preserve the look and feel of your RTL or look and feel of your design. No one likes, if you have coded your design in a certain manner, you wouldn't like to come and see that the tool completely messed up the same. So you would like to preserve the look and feel. And finally, on the verification side, you want to simulate and verify as much of DFT as possible early in the design cycle or in RTL. So things like equal verification. You have your IJTech network. You want to verify that network. You have SSN bus already in there. You want to run some tests to verify the SSN bus. You have logic-based implemented here. You want to run some self-tests to make sure that the controller is working correctly. Then you also want some of the debug capabilities. So if something is not working correctly, how can I figure out what is wrong and how do I take corrective measures? So some way to also get an impression of what will be your ATPG test coverage, what will be your pattern count. Are there some outlier blocks that need special attention? If you can get that information early in the design flow, you can then take corrective actions, corrective measures to improve the overall testability of your design. So let's look at the DFT shift left evolution. So if you look at 2 decades back, 20 years back, right? Most of the DFT was implemented or inserted and implemented in the gate level. So you go through synthesis, you insert all your DFT, then you actually do some incremental optimization to make sure that your timing closure is still there. So you want to make sure that design closes timing. And then finally go and do generate ATPG patterns. But over the last decade, things have changed. Most of the DFT insertions, like memory-based, the repair IP, the IJTAG, OCC, logic-based, test compression, SSN, all these things are now inserted at RTL. So you have the opportunity to implement that, verify those, and see how those are working early in the design cycle. The only thing or the few things that were still done at the gate level are things like test point insertion, wrapper cell insertion, or X-bounding logic, or scan stitching, right? What we are doing now is providing tools so that you can actually also do test point analysis and insertion, wrapper analysis and insertion, and X-bounding analysis and insertion at RTL. So you don't need to wait until the gate level. So this allows you to write out the RTL after all those DFT are implemented. You can do your equivalency checking to make sure that the design is still working. And you can also, in some cases, verify how, like whether they are working correctly or not. So that reduces your iteration time, because if you insert things at gate level and you see things are not working, you have to go back to RTL, make some changes. But this allows you to look at your design, to implement all the DFT and verify that DFT at RTL. And there are other options where you can do these things as part of synthesis, but this is even better as it allows you to write the RTL. And it is not, the output that you get is an RTL, which you can still simulate and verify before you go to the synthesis process. So the last three, the test points, wrapper analysis, and expounding, this is what is part of a new tool called RTL Pro that we announced yesterday at ITC. So what are some of the key features of RTL Pro? It does a quick RTL complexity analysis and reporting, so you know what are some of the complex RTL modules that you have. It also does an analysis of the RTL to let you know whether that design is suitable for test point insertion in RTL or not. Because there are certain designs, if it is completely very control heavy, everything is in the control logic, RTL test point insertion may not be, you'll not be benefited from that. You may have to do some parts of it at the gate level. So it actually tells you, advises you whether you can do the test point insertion or some of the other analysis at RTL or not. And then it does the analysis insertion of the test points, wrapper cells, and expounding logic. And this is actually consistent with some of the RTL DFT capabilities that exist across all the Tessent tools. So today, our tools already allow you to do design rule checks. It allows you to do design editing. And it also generates things like IJTAG gray box that simplifies the view of your design, that actually allows you to speed up the simulation. It also, as I mentioned, preserving the look and feel of the RTL is very important. So it already does that. And we try to minimize the changes to the blocks where you are not touching. And it also, the tools are capable of handling complex Verilog and system Verilog constructs that are in your design. Things like system Verilog interfaces or generate loops. And under the hood, the tools have the quick synthesis engine that allows you to quickly synthesize your RTL, do scan stitching, and run ATPG so that you get an idea of what your test coverage and pattern counts are. And this is much more accurate than some of the estimates that you can do at the RTL today, because it doesn't match with reality. So in summary, so the productivity challenges will continue because of the design, technology, and system scaling. The innovations in RTL, DFT implementation, and verification will continue to improve, which actually will allow you to reduce the time to market. And then Tessent RTL Pro extends the Shift Left DFT strategy by moving the implementation and verification to RTL. Thank you.